Hi and welcome to this Leaving Certificate Applied Maths video. In this video, we're going to look at vectors. So as part of this video, we're going to look at understanding the idea of the magnitude of a vector. We're going to resolve vectors into their I and j components. We're going to look at the dot product, so multiplying our vectors. We're going to find the angle between two vectors, and we're going to look at identifying if vectors are perpendicular. So this video is suitable for all applied math students. However, our focus in this video is going to be on the ordinary level questions that have appeared to date. The reason for that is we have only seen in the three ordinary level papers we have, 2023, 2024, and then the sample paper, we see that this vector explicit question, while in the higher level papers we've seen, which are for the higher level sample, the 2023, 2023 deferred and 2024 papers, vectors have come up, but they've been integrated into other topics like projectiles, impacts and collisions. And what we'll do is we'll explore that individually within those topic videos. So before we begin, it's good to know that some of what we're talking about today is available in your log tables. It's not perfect. It may not be exactly as we name it in applied maths, but it's here. So in this case, so this is from page 17, we have a section called vector operations, and it gives us two vectors here, v1 and v2, and they're defined as x1i plus y1j for vector 1, and v2, vector 2, is x2i plus y2j. So then we have this formula here, and that's called the norm. Now what we refer to that as is the magnitude. So there's our formula for magnitude. It is just a rearrangement of Pythagoras, but it's good to know that we have that explicitly in our log tables. We also have this piece here, which is called scalar product, which we refer to as dot product. And we're going to discuss the dot product in a little bit more detail. So as well as having the dot product there, we can also see that we have the formula which helps us get the angle between two vectors, and it's this piece here. So if we combine those two together, we can get an angle between two vectors. So this is what it looks like. However, that right hand side is the dot product, so we could rewrite that as our v1, v2 dot product piece since they are equal. So we have a few different versions of that formula. It's not maybe exactly like you will have seen it as you're learning it, but it is there. And it's nice to know that it's one that you can look in the log tables and don't have to learn off by heart. So let's run through some notes about what we need to know for our vector section. So the first is our magnitude of a vector. So like I said, that's available on page 17 of our log tables, but in simple terms, it's saying if a vector is ai plus bj, the magnitude, and we use those two straight lines, which means size in maths, size of a line or size in general, size of an angle. When we say size of a line, we say length. So often we can see those lines used to represent length. For us, the magnitude and length of a vector means the same thing. So we then talk about resolving our vectors into I and j components. So if we take an angle here in a triangle and go back to our basic trigonometry, we have the hypotenuse, and that's the magnitude of a vector. So if we think of this in terms of our vector, I'll just put on color so we can see. So if this were my vector and we put an arrow on it, this is the magnitude. Okay, so the hypotenuse is the magnitude. And then that vector can in turn be broken into an I component, which is the bit that's horizontal, and a vertical component, which is our j component. So rather than having this diagonal, we can say it's so many across and so much up. So that's how we deal with our vectors. So I represents across, j represents up and down. So if we were to work with our sine, cos, and tan, we end up with the I direction is opposite equals hypotenuse times cos. So just where that comes from, if we start with cos of this angle is adjacent over hypotenuse, and then we multiply both sides by the hypotenuse, so the adjacent side is going to be the hypotenuse multiplied by cos. And the adjacent side, we can see, is the I direction. So that's going to be hypotenuse times cos of the angle. Sorry, I have theta in there, but that should be angle A. For the j, we have something similar. It's the hypotenuse times the sine. So again, if we have sine A, and that is opposite over hypotenuse, we can rearrange that such that opposite equals hypotenuse times sine A. And the opposite side is representing our j direction up here. So that gives us our j piece. And then if we want the magnitude, let me just get rid of some of this writing so you can see it. So if we want the magnitude as v, or sorry, if we write the magnitude as v like this, so the magnitude of our vector, we can rewrite this whole thing in simple terms that the vector can be written as the magnitude of the vector times cos AI plus the magnitude of the vector sine AJ. Now that's only true for where the angle is sitting here beside the I-axis or the horizontal. If the angle was given against the vertical, okay, so let's look at that. So if I give you another angle B, if that were the case, then this side becomes the opposite and this side becomes the adjacent. So remember, our opposite and adjacent really depend on where that angle, the marked angle, is. So this will work for the majority of cases, but it will not be absolutely everything, okay? So we still need to think about where is our angle. So in simple terms, that's our I and J direction, but just to be aware that only works when the angle is against the horizontal. So let's talk about the dot product. So when we're multiplying vectors. So when we multiply two vectors together, we get what's called a scalar number or a real number. So we're not left with a vector. So if we multiply two vectors, we can see it AI plus BJ times CI plus DJ, and there's always that dot. That's what we call it dot product, product meaning multiply. We get A times C and B times D. So you multiply the I pieces together plus then multiply the J pieces together. That includes the signs. We have a version of this on page 17 that's called our scalar product. If you want to then move on to get the angle between two vectors, we have this formula here. So the cos of the angle is equal to the dot product of the two vectors over the magnitude of the two vectors multiplied together. And again, we have a version of that on page 17. What I'd say is if you think you will use page 17 in your exam, get familiar with it and how to work with it. If you're happy learning these off by heart, that is absolutely fine, but we don't see them maybe a huge amount. So it is important that you do know them and know them properly if you're going to learn them off by heart. So then I've left the angle between two vectors up there, and the last thing we're going to talk about is perpendicular vectors. So two vectors are perpendicular if and only if their dot product is equal to 0. This is really, really important. And we could see this maybe coming up somewhere in a calculus question, even at higher level. So it's a really, really important little idea, and it's one that could stop you. It's one that actually you may not be able to move forward with. We saw it on the 2023 paper as part of the projectiles. So just be very, very aware of this. This is not in the log tables. You can kind of figure it out, but it's easier to just remember it. So x, the vector x is perpendicular to the vector y if their dot products equal 0. And this arrow here basically means it goes both ways. So if they're perpendicular, then their dot product is 0. If their dot product is 0, then they're perpendicular. So the converse of that is also true. And the reason that that is the case is because perpendicular means 90 degrees and the cos of 90 equals 0. So if we go up to this formula, which is why I've left it on the page, we can see that if the cos is 0, if the cos of 90 is 0, so let me put in 90 here. So if the cos of 90 is 0, that means that this thing here has to be equal to 0. Now, a few ways to think about this. The bottom line cannot be 0 because we cannot divide by 0. It is impossible. You will get an error. It is undefined. You cannot divide by 0. So these two bits here, the magnitude of vector x and the magnitude of vector y, they have to give a number. If they do not have magnitude. If they do not have a size, they don't exist. So we can't really talk about them being perpendicular to a vector that doesn't exist. So they have to exist as a vector. So the bit that will equal 0 is this top line here. So that's where we're getting this idea of the dot product equaling 0. So you can figure it through with that formula, but you want to, in an exam, be able to work very, very quickly and pull that 0 out. One of the things that might help with this is understanding the dot product. So often students learn the dot product and they work with the dot product, but they don't really have an understanding of, what is this? What does this number represent? What am I doing? So when we do our multiplication of two vectors, we get this scalar or number answer. And most students are relatively okay with that. So they don't put in their I's, they don't put in J. But what is the number we get? What does that mean? What does the answer represent? So there's two things we can tell with this answer. The first is the alignment between the vectors. So think of this, of how they're lined up. So if the dot product is positive, the two vectors are pointing generally in a similar direction. So they're less than 90 degrees apart. So think about what that would look like. So we'd have maybe a vector here and a vector here. So that's our little angle between them. So that means actually they're roughly in the same direction. If it is 0, we know, we just talked about it, that they are perpendicular. And if it's negative, then they're kind of pointing in opposite directions. So you're going to get something like that. So the angle there is going to be bigger. So that dot product is a measure of how aligned the vectors are, so how they're pointing. So to keep that in mind can really help with the perpendicular vectors. The dot product equals 0. It will help you to remember that. So the second thing it kind of represents is the idea of the magnitude of projection. So the dot product can also be thought of as a measure of how one vector projects onto another. So for example, if you want to know how much force in a certain direction is acting along another direction, the dot product gives you that value. So that's a more practical use for it. So when we think of our vectors as something, practical in the real world, like forces, so that'll help you get a sense of what's going on. So hopefully that helps you to understand what we mean when we calculate that dot product. So let's start with our first example. This example is from the sample ordinary level paper, and it's question 1 part A. So a displacement vector B has magnitude of 15 kilometers and a direction alpha north of east. And we can see that in the diagram where tan alpha equals 4/3. A second displacement vector C has a magnitude of 10√3 and a direction of 60 degrees south of east. Again, we can see that. So interesting, they've given us the magnitude of both and then something about the angle. So they haven't told us the actual angle in the first case. They've just told us the tan of it, but in the second case, they have told us. The direction there, south of east, means go east and then go south. So south of east. So it is 6 degrees lower or south of the east direction. But we have a lovely diagram to help us. So express B and C in terms of their unit vectors I and J. So one thing you can do when you have the diagram is kind of make sense of it. I think, when you're getting into higher level questions, you want to be able to move much quicker. But to get used to it, we can see if this were a triangle and there's our alpha, this side here is our opposite. And we said that our opposite side is going to be the magnitude. So the magnitude of B, and the opposite is sine. And it's sine because think of your formula for sine. Opposite over hypotenuse. Then this side here, which is my I, is the adjacent, and that's going to be the magnitude of B cos alpha, because it is the adjacent side. So that looks like this. So our vector B is 15, which is the magnitude of B, cos alpha I plus 15 sine alpha J. So in order to fill in our cos alpha and sine alpha, we're going to go back to the second bit of information they gave us, which was about tan. So they told us the tan of the angle. So in this case, alpha was 4/3. So what we're going to do is we're going to sketch out a little right angle triangle. When you get good at this, and you may be able to do that in your head and work this through, and that's absolutely perfect. But when you're starting, visualization is great. So tan, if we think back to our formulas, whatever way you work it, is opposite over adjacent. So the opposite side is 4 and the adjacent is 3. And then we're left with the hypotenuse. You can use Pythagoras here, but hopefully most students know that this is a 3, 4, 5 triangle. It's our special triangle. We have a few of them that you'll meet up and down, but if you need to calculate it, you can. That means we can now work out our sine, which is opposite over hypotenuse, and cos, which is adjacent over hypotenuse. So then when we come along here, we're able to plug in that information for our alpha, for our sine alpha and for our cos alpha, and we're able to work out our value for our vector b. So b is 9i plus 12j. Just be careful with this. Often I see students when they're starting off putting in this for alpha. So we're changing cos alpha to 3 over 5. Okay, and we are changing sine alpha to 4 over 5. So you're subbing in for sine and for cos in this case, not the angle. So just be careful. Now, for C, it's a little bit easier. So I'm just going to clear this because they've given us the angle. So we don't have to mess around with the right angle triangle. However, look at what's happening here. For C, you're going across, but then you're going down. So that down means we're going to have negative in the j direction. So this is going to look like 10 root 3 cos 60i minus 10 root 3 sine 60j, because it's going down. So you have to keep an eye on your signs here. Okay, I know resolving can be tough as you begin it, but you have to keep an eye on your direction. Remember, we have a diagram here, so we're not just trying to rely on the words. You can go straight to your calculator for this or use page 13 to help you. And we get final answer 5 root 3i minus 15j. So part 2 asks us to calculate the dot product. So remember, we have a version of the dot product here. It's this bit that we're looking at, given that v is this and v2 is this. So what that's telling us to do is to multiply the 9 by the 5 root 3 plus the 12 by the minus 15. And we do use those signs. So this is what it looks like when we do the dot product of b times c. We multiply the two I bits together plus multiply the two j parts together. And you are including the signs. That gives us 45 root 3 minus 180. That's kind of as simple as it can be in surd form. And if we go to decimal, that's negative 102.06. So a lovely straightforward question once you know what you're doing. So part 3 tells us a third displacement vector d is perpendicular to b. D is minus 4i plus kj. Calculate k. So in this case, we have to remember that if vectors are perpendicular, their dot product is 0. And that's what we're going to use to solve. Because we have an unknown, we're going to set up an equation and we're going to solve for k. So since the vector b is perpendicular to the vector d, then we know that b times d, that dot product of b and d, should equal 0. So b I have put up here. We worked it out in the last part. D was given to us. And that's going to look like this. The I bits multiplied together. So 9 times minus 4 plus the j parts multiplied together, 12 by k. And that should all equal 0. So that gives us minus 36 plus 12k. 12k equals 36 and k equals R3. So that was about half a question on the sample paper. So it gives you a sense of what could be asked. Like I said, at ordinary level, we're seeing this as an explicit question. At higher level, they're integrating the same questions, but just into other topics. So example 2 is from the 2023 ordinary level paper, and it's question 3. Two vectors, q, which is 6i plus 8j, and or, which is minus 4i plus 3j, are shown on the diagram below. Q makes an angle alpha with the positive direction of the y-axis, and or makes an angle beta with the negative direction of the y-axis. So we can see that all on the diagram. And then the first question is to calculate S, where S is minus a half Q minus OR. So what we're going to do is we're going to sub in Q and OR like we would in algebra, but we're going to use our brackets. So it's going to look something like this. S is equal to minus a half. Instead of Q, we're putting in 6i plus 8j minus, and instead of OR, we're putting in minus 4i plus 3j. We're going to apply that half. So a half of 6i and a half of 8, minus a half times 6, minus a half times 8. And we're left with minus 3i minus 4j. And then when we look at the second bracket, minus 4i plus 3j gives us a plus 4i minus 3j. Now all that's left to do is to tidy up, add the I terms together. So if we have minus 3i and we add a 4i and then we add the j bits together. So that gives us final answer of 1i minus 7j. And then they ask us to draw S on the axis shown. So 1 is over here and minus 7. So it's 2 boxes each. So it's down to here. So we bring it to there. So it's going to look like this. And that's 1i minus 7j. So make sure that you label it. So you can label it with just an S. I've put the vector on it as well. So part 3 asks us to calculate the magnitude of Q and the magnitude of OR. So you are expected to know those two straight lines. They mean size in general in maths. And the size of a vector is called the magnitude, or we can think of it as the length of the vector. And the formula, we have a version of this called the norm on page 17 of our log tables. So for Q, that's going to be the magnitude of Q equals the square root of the I part squared plus the j part squared. So 6 squared plus 8 squared. And that works out to give us 10. For OR, it's going to be the square root of minus 4 squared plus 3 squared. And that gives us 5. Now, because we have the diagram, you could work through and use Pythagoras on the diagram. But remember, for higher level, this could be part of a question. We see magnitude asked a lot in uniform acceleration and also in projectiles, where the magnitude of velocity is speed. So when you're asked for speed, you're being asked for a magnitude. So bear that in mind. It can appear in more than just a straightforward explicit vector question. So part 4 asks us to calculate alpha and beta. Now, alpha and beta are shown on our diagram and we haven't discussed it up to now. I'm going to show you kind of how this comes about and then what we can use as a shortcut. So for alpha, what I'm going to do is I'm just going to create the triangle here on our diagram. We have the hypotenuse here and we've worked out the magnitude earlier in the question and it's 10. This is the opposite side and reading from just the axis, I can see that it's 8. Here's the adjacent side and again, reading from the axis, I can see that that's just a 6. So if we were working with trigonometry, we can use sine, so opposite over hypotenuse, cos, adjacent over hypotenuse, and tan. So any of them will work because we have all the information. However, we tend to work with tan because it doesn't require the hypotenuse, which means you don't need the magnitude. So if you haven't worked out the magnitude, it's fine. So what we're going to have is tan of alpha is equal to 8 over 6. So alpha is equal to tan inverse of 8 over 6, which is 53.13 degrees. Now, the shortcut, or in general terms, what we mean by opposite over adjacent is the j component over the I component. So once you put the j component over the I component, you effectively have the tan of the angle. Now, that's a nice short, quick way we can work. So if we don't have a diagram, if we're in projectiles or if we're in calculus and we're being asked to do something with the angle, we can work with that. So let's try that shortcut over here for our beta. So for beta, we're going to say tan of beta is equal to the j component over the I component. So it's going to look like this. Notice that we don't include the signs, and that is on purpose because if you've studied your trigonometry in maths, you'll know that sine, cos, and tan are positive for acute angles. So because this beta is very clearly an acute angle, we're only dealing with the positive. So we're taking just the numbers. Think of it in terms of our triangle. We would say simply this length is 3 and this length is 4. We wouldn't get into the idea of that length is -4. It wouldn't make any sense. If we were to include that negative, it would end up giving us this obtuse angle. So because most of the time, and this is back to what we talked about at the start of the video, most of the time you're going to be working off the y-axis or the x-axis or the horizontal. So it'll just give us the j over the I. It may need a bit more work, but in general, that is going to give us the angle that we want. And generally, we also are going to be looking at an acute angle, which means we're ignoring the signs. And we're doing tan inverse of 3/4, which gives us 36.87 degrees. I didn't simplify on the left, you could have, but just note that that actually simplifies to 4/3. And we have the tan of 4/3, the tan inverse of 4/3 and the tan inverse of 3/4. And those two numbers are actually related because they are the opposites of each other. Those angles will actually add to give me 90 degrees, and you can try it now. We can think back to our idea of perpendicular lines in coordinate geometry. Perpendicular lines, their slopes are opposite reciprocals. What that means is we flip their slope and change the sign. Tan and slope are effectively the same thing. Okay, rise over run. So when we're doing our tan here, it is effectively like we're working with our slope again. So bear that in mind. And that is going to feed us into our next question, which asks us to calculate Q dot R, which is the dot product of Q and R. So using our log tables, so it's this version here that we want. Our dot product is going to be multiply the I bits or the I components by the j components, our I components together plus the j components together. And that gives us -24 plus 24, which gives us 0. So we talked about this earlier in the video, but it didn't ask. But what does that say? What does that mean by Q and R? So it's telling us basically that they're perpendicular to each other. And we could see that if the two angles alpha and beta added up to 90, then what was left in the middle must have also been 90. So again, nothing to do with the question, but a nice observation when you're studying to see all these things and how they interact. It's a nice idea to think about, well, if I end up with two angles where, you know, the numbers are the same, but we flip the opposite and adjacent, how does that work? So if we think of our triangle, effectively alpha and beta here and here. Let's do a little 5, 4, 3 triangle. So if you look at the cos of alpha, that is 4/5, but the cos of beta is 3/5. And if you look at the sine of alpha, it's 3/5, and the sine of beta is 4/5. So we're getting a bit of a connection here. Okay, and then if we look at tan, which is the one we care about, so the tan of alpha is equal to 3/4, and then the tan of beta is equal to 4/3, and we can see those reciprocals. And because they are reciprocal, we can see that they're the other two angles in a right angle triangle, and they have to add to 90 degrees. So there's a lovely kind of connection you can do here, understanding how sine, cos, I mean in particular for us, tan interact when two angles add up to 90 degrees. And if, like these were, they're hanging off that y-axis, that x-axis, they add to 90, they have to leave our 90 in the middle as well. So the last part of this question was actually not necessarily very tricky, but there was quite a bit in it for an ordinary level question. So it tells us to calculate the values of k and t such that k times the vector q plus t times the vector r equals -10i plus 20j. So just like we've seen already, you're subbing in for your q and your r, and it's going to look something like this. So a lot of students can get to here and then kind of get stuck. So what we're going to do is we're going to multiply it out. I and j will always be last. So k by 6i is going to give me 6ki. K by 8j is going to be 8kj, and so on. So it's going to look like this. Now, this equation here, it's called an identity. And what that means is effectively we can solve two little equations within one equation. And you meet identities when we're in algebra. You might call them unknown coefficients. We meet identities when we're working with rational and irrational numbers together. We can meet identities when we're looking at complex numbers. And a kind of giveaway for us that it's an identity is if you feel you have too many unknowns to solve for one equation, because our general rule in maths is one equation will solve for one unknown. If you have two unknowns, you need two equations, and so on. So here we have a k and a t that are missing, and we've only one equation. So it feels like there's something missing. So what we're going to do is we're going to split this into two equations. So we're going to split this into just the I terms and the j terms. Because effectively the I terms have to add together on the left-hand side to give me minus 10. And the j terms on the left-hand side have to add up to give me plus 20 on the right-hand side. So we can balance that. So the I terms, we're going to say that this term plus this term should give me that term, because I and j terms don't interact. And that gives me my first equation. My second equation is coming from the j terms. So we can say those plus 8kj plus 3tj should equal 20j. Effectively, for each of those, we're simply going to ignore the i's and the j's. So for the I terms, we get this equation. I can divide that across by 2. So I'm going to call that my first equation. I'm going to do the same with the j terms, get rid of the j's, ignore them. There's nothing I can do here. So I'm going to call that my second equation. And this is how we've created our two equations that we do need to solve for two unknowns. Okay, so that bit is true, but often we can find our two equations sitting in one identity. So watch out for those. They're where we have elements that don't mix, so can't be added. So x squared terms, x terms, and constants, they cannot add together, which is why we get it. For complex numbers, we have our real and our imaginary cannot add together. Here we have our i's and our j's cannot add together. So now we just have a simultaneous equation. I'm going to multiply top by 3 and the bottom equation by 2, which gives us these two equations. Watch out when you're multiplying to make sure you do the constant at the end. I've made the t's eliminate, so they're gone. That leaves me with 25k equals 25, so k equals 1. I'm going to go back. You can use either equation. I'm going to go back to equation 1 and sub in my value for k. So that's 3 times 1 minus 2k equals minus 5. So that gives me minus 2t equals minus 8. Watch your signs, bring that 3 over. Divide both sides by minus 2 and we're left with t equals 4. So quite a bit of work in that for an ordinary level question, but a good one to see and a good one to practice. So our last example in this video is example 3. It's the 2024 ordinary level question 2, and it's part 1 to part 6. So 2 tugboats P and Q pull a ship. The pulling force P has a magnitude of 26 kN, which is kilonewtons, and direction theta degrees south of west. And they've told us that tan theta is equal to 12 over 5. South of west is shown on our diagram here. So bear that in mind when we're doing our resolving. So they've given us a force Q as well. So P, we're going to use that idea of resolving our vector, our cos and our sine. However, given this, so think of your axes here. It's going down and to the left. So there's my i's. Here are my j's. So here, both the I and the j are negative. So it's going to look like this. Minus the magnitude, so 26 cos theta I, minus the magnitude, so minus 26 sine theta j, kilonewtons. Again, we've been given a little triangle. Let's work with that. So we've been told that tan of theta is 12 over 5. So that means the opposite is 12, adjacent is 5. You can use Pythagoras, but again, this is another very common right angle triangle. It gives us 13 as the hypotenuse, and then we can get our sine and our cos. Absolutely fine to work that through with Pythagoras, and eventually you may not need to draw these little right angle triangles at all. So that gives us the vector P is going to be 26 times 5 over 13i minus 26, 12 over 13j. It's all kilonewtons. And our final answer for P is then minus 10i minus 24j kilonewtons. Okay, if you didn't put the kilonewtons in, that's fine, but it is representing a force. And if we're asked anything practical in the question, we need to remember that. So now we're being asked to do the dot product of P and Q. I've put P up there and we had Q given to us here in the question. So I'm going to use our dot product piece from here. And that means the I coordinate or the I components together plus the J components together. So it looks something like this. Working that through, it's 100 plus 144, and it gives us 244. So then calculate the angle between the vector P and the vector Q. So we're being asked to work with the angle between two vectors formula, which is effectively like a combination of these two lines. Okay, so for us, it's going to be the dot product divided by the magnitude of P times the magnitude of Q. And you can, if you want to start off with this bit here. So this is effectively the dot product. So this bit here we know is 244. So you could say 244 equals magnitude of P, magnitude of Q, cos theta, and then like rearrange as you need to. That's fine. Whatever you want to work. I've actually used A here for the angle because theta was used as the angle for P to the horizontal. So I filled this in. So cos of our angle A is 244 over 26 times the magnitude of Q. Now we actually don't know the magnitude of Q, so we're going to have to work that out. So the magnitude of Q, we're using this formula here. And it's going to be the square root of minus 10 squared plus minus 6 squared, which gives us 2 root 34. I am going to leave it in third form. I'm going to plug that in, and we can tidy that up, or you can leave it as is. I'm lazy. I like to leave mine as is and just put that into the calculator as my cos inverse. And we get a final answer of 36.42 degrees. So we have 3 more bits left to do on this question. So the first is just asking us to calculate P plus Q. So this is like, well, I'll talk about it because the next part asks what it means. So let's just add them together first. So we're adding, so I have P here plus Q, and you add the i's with i's and the j's with j's. So minus 20i minus 30j. So what does the vector P plus Q represent in this context? So this is, again, like what I was saying, we're talking about a pulling force. So we add P and Q together, we're getting what's called the resultant force, okay? So the resultant, what happens when you add these two together? So if these two are pulling, it's what direction the ship they're pulling will move. That is effectively what it means, okay? Because we have this idea of a direction. So the resultant force, so what way is the force moving on the boat? Okay, and then they ask us to get the magnitude of this. So we are applying the magnitude after we've done P plus Q. So we're applying it to our answer from part 4. And that works out as 36.06 kilonewtons.